evening and welcome to Physics Department and Astronomy Program's 37th Annual Bunyan Lecture. I'm Professor of Physics of the Faculty Chairman of Astronomy Program, which has been conducting this lecture series since 1979. We had a few breaks, particularly COVID, but now we are resuming again. Before introducing our speaker tonight, I want to say a few words, as is customary, about Mr. Bunyan, whose generosity supports this lecture series and some other activities of the astronomy program and physics department. Mr. Bunyan was a long-time research scientist at the Stanford Hubble Institute, and at the end of his life, after some careful consideration and examining many possibilities, and some gentle persuasion was late Professor Ron Bracewell of electrical engineering, he decided to give his life savings to the astronomy program for conducting this lecture series. And this endowment has been helpful in maintaining and upgrading sometimes our student observatory, and for a while we were a member of the 10-meter telescope. But most prominent in Mr. Bunyan's mind was that establishment of this lecture series with the purpose, and I quote, bringing to the general audience accounts given by renowned scholars about the workings of the cosmos, its galaxies, stars, planets, as well as the dawn of life and destiny of man. A tall order and something, but really dealing with a couple of major questions in almost everybody's mind, which is the beginning of the universe and beginning of life. Well, astrophysics has progressed a lot since then, and the landscape of the field has changed a lot. When Mr. Bunyan wrote those words, we were doing optical or other electromagnetic observation by electromagnetic radiation of ordinary matter, but nowadays we are mostly dealing with multi-messenger observations, and we are dealing mainly with what we call the dark sector, dark energy, dark matter, which we don't know much about either one of them, and black holes and planets. So, and the Bunyan lectures over the years have reflected this change too. But for more appropriate for tonight's lecture, I want to quote another thing Mr. Bunyan wrote, and he later on in his will he says, astronomical observatories will go into space and bring some crucial problems, solve some crucial problems of cosmology, and bring fresh ideas of the mysteries of the universe. Okay, so we are grateful for that with John Mather, astrophysicist at NASA Goddard Space Flight Center and a longtime friend, who has agreed to be our 37th Bunyan Lecture. But I was thinking about introducing John. I said, well, this should be easy. Has a lot of accomplishment and awards. But when I started reading the CV, I thought, oh my God, this is difficult. So many of them, so many accomplishments, so many awards. But I'm going to do. So I'm going to give a very brief version of it. Okay, John received his bachelor's from Swarthmore, 1968, and a PhD physics at UC Berkeley, which we won't take against him. He has spent most of his career at Goddard, first as a postdoctoral fellow at the Institute of Space Studies of Goddard, and now as a senior astrophysicist and senior project scientist of the James Webb Space Telescope, JWST, which will be the topic of this talk tonight. As a postdoctoral fellow, a young, new researcher, he led the proposal efforts for a big project called Cosmic Background Explorer, or COBE for short. And later he became that project's scientist for that project. He successfully managed that program and was able to make wonderful observations. And one of it that he presented at one of AES meetings for the COBE team, he showed a spectrum of what we call cosmic microwave background radiation, which is leftover radiation from Big Bang. The main signature of that universe started with a Big Bang. And this was such a fantastic observation that they could show that within 50 parts per million, the spectrum of this radiation was exactly a black body. This is what you expect the radiation from Big Bang to be. For this thing, there was a rare occasion on the AES meeting. He got a standing ovation. Of course, in addition, this was a great accomplishment that in 2006, he received Nobel Prize for it and shared that with George Smoot. As I said, there are many other awards, probably more than 50, several hundreds of publications, equal number of community service meeting committees that he has served and has led for many new projects. He's also a member of National Academy of Sciences, American Academy of Art and Science, and is a life member of Optical Society of America and many other societies. So once again, it gives me great pleasure to present to you Dr. John Madden, who will talk about opening the infrared treasure chest of JWST.
Thank you, Vi. Is the microphone working? Can you hear me? Okay, thank you. Thank you for the lovely introduction, and I always am amazed that I think they're talking about me. Because, as you see on the chart up here, it takes thousands of people to do these space missions. So when I talk with you about what we are doing, it's always a we did this, not I did this. And however, I get to be the one to tell you about it today. So I want to tell you about the James Webb Space Telescope, which is a joint project of NASA with European and Canadian space agencies. It has taken 20,000 people for us to finish this project and get it up into space. And there are about 10,000 professional astronomers in the world, and they all have a chance to use it. And so we're going to show you some of the results we got so far, and tell you a little bit about why everybody is so excited about it. But anyway, thank you for the invitation to come and show these marvelous things that our team has prepared. So, but however, stepping back into time a little bit, what are the questions people care about? So, where did we come from? Well, that's a pretty generic question. What's the history of the universe? And of course, everybody wants to know, are we alone? Is there other civilization nearby or not? And how far away are they, assuming that there are some out there? A very close to home question is life something that could only happen because of an extremely rare coincidence? Or the opposite guess, which is my preferred guess, is that it always will happen when given the proper circumstances. So that doesn't tell you about civilization, it only says life, because there's lots of forms of life. But at any rate, and then people want to know, can we travel to the other stars? And probably not, I'm sorry to tell you, but that seems to be the deal. We can travel to Mars. We know how to do that. We haven't done it yet, but we know how, in general. But astronomers, I like to say, we see everything twice. We take a picture, and then we draw something in our imagination, and maybe even make a movie of what we think happened. So now we can travel as far as you like, as fast as you like, with imagination. So a couple of thousand years ago, the poet Lucretius wrote on the nature of things, and here is a little bit of it. He was aware of the atomic theory, because there was some evidence even back then that things might be made of tiny particles. An atom means indivisibly small particle in Greek. At any rate, how would they know? Well, a water glass will evaporate, and so the water has turned into something invisibly small. That was one idea. So they had the idea, and this particular bit shows that they understood, at least some people did, that little bits could stick together to make big things, and then they would change around and then disappear. Then the poet even knew something about linguistics, we giving names to things, and then they disappear. So there it was 2,000 years ago, so it's basically still true as far as I know. So how did I get to be here in front of you? I started out here. This is a research farm of Rutgers University in far northern New Jersey, about a mile from the Appalachian Trail. And that's where I was as a child. And my dad was a research professor studying dairy cows. And so in 9th grade, I learned statistical analysis from him, but I didn't decide to study dairy cows. It was a good place to be a beginning scientist because the bookmobile came around every 2 weeks and I read all the science books that they had. And sometimes they sent away to the state capitol to get books about how to make telescopes. So that was me. I was obsessed with those things when I was about 10. So I'm still doing it. My childhood dream is still alive. Maybe I still am a child. At any rate, that was then. So coming back to what do astronomers do, we have our ways to look back in time. You look at something far away, you see it as it was when light was sent out to you. You don't think about it, but each of these things we call eyeballs is actually a time machine. We see things as they were, not very long ago or very long ago, depending on what you're looking at. If you could see the nearest other galaxy, you would be looking about several million years back in time. If you could see all the way back to what we call the Big Bang, it's almost 15 billion. In my old chart, it's actually 13.8 billion years you can look back in time. And that's because we know the speed of light and we can survey the universe. So how do you survey the universe? Well, we do it this way. The ancient Greeks would have done it this way too, and they did. They actually drew triangles and they calculated the size of the Earth. They calculated the distance to the moon, and they got it about right. They failed to get the distance to the sun because their equipment wasn't quite good enough. But at any rate, they understood the idea that you could survey, and they would have understood the second idea about standard candles. If I have two objects in space and I say, I believe they're identical, but one of them looks fainter than the other, we say we know how to calculate the ratio of brightnesses as the square of the ratio of distances. So that was known, and so that's our basic method to survey the distances. And it works. We have one other thing we want to know, which is how do things move? And so a few things moved perceptibly across the sky, and you can tell. Even with your own eye, you can watch the moon moving through the constellations in the course of one evening. The rest of them move too slowly to notice mostly. But we have one thing that we can do that applies to even the most distant objects. So astronomical objects have atoms and molecules and things in them, and they send out or absorb light at particular wavelengths owing to the chemistry and quantum mechanics. So if we spread out the light of the sun into a giant rainbow, it has dark bars across it due to the different chemical elements in the surface of the sun. And if we do that for a distant object, like another star or a galaxy, with similar patterns, but the wavelengths often are increased and by some factor. And we usually interpret this as saying the object is running away from us at some speed. And now we can calculate the expansion of the universe. And that was done in 1929. So it's a graph made by Edwin Hubble, the same guy we named the telescope for, in 1929. So this is the first time we actually had strong evidence that the universe has an age. Because you see there's a trend here. The farther away they are, the faster they're going. If you divide the speed of motion into the distance that you think you have, then you get the age of the universe. So he got the wrong answer. It was 2 billion years. It's actually 13.8 because he didn't actually have the right calculation of distance. So 1929. And by the way, we have now named it the Hubble-Lemaitre law for this straight line on this chart because Georges Lemaitre was a Belgian priest as well as having a PhD in math from MIT. he applied Einstein's equations and he predicted that this must be true. Einstein made fun of him and said that couldn't possibly be right. That was Einstein's biggest mistake, as he said. So, okay, so Einstein has been wrong. It's very rare for us to catch him at it. And by the way, I still have friends who think they're going to prove that Einstein's relativity is wrong. It's not working. Anyway, Georges Lemaitre did not claim credit for all of this, but we give him credit anyway. So what happened then? Well, it was mentioned that I went to Berkeley, and while you all were having a football game with Berkeley, I was measuring an acoustic wave propagating through the Earth because we were doing a nuclear test in Alaska, and I set up my little extremely simple seismograph, and I measured the seismic wave from that nuclear test while we were all playing football up the hill. But more to the point, I tried to measure the cosmic microwave background radiation as a graduate student. So I did make a measurement with Mike Werner from Mountaintop in California on White Mountain. And then that worked, but then we said, we'll try the next one. It was a measurement of the cosmic microwave radiation from a balloon payload. And that one didn't work. So I got to write a thesis about one boring experiment on the ground and a failed experiment in flight, and they let me out. And then I was in New York City, had a postdoc at New York at the Goddard Institute for Space Studies. And I was there when NASA said, we want proposals for new satellite missions. Hey boss, my thesis project failed, we should try it in outer space. So that became the Cosmic Background Explorer satellite, because he knew what we should do. We called up our friends, we wrote a thin proposal when we said we've got an idea. And it turned out that was a good idea. So 15 years later, we made the presentation that Vahe mentioned with a curve that matched exactly the idea of the Big Bang. So I'll show you the satellite itself. There it is, more or less as it would have been if there were light on it in that way in outer space. It had 3 instruments, one of which was my thesis project grown up and working correctly. And we did indeed measure the spectrum of the Big Bang, which is to say the color or the intensity at each different wavelength, and it matched exactly, as he said, with what we expected. We also made a map of the hot and cold spots. We made a map of the entire sky using a millimeter wave receivers, and this is the map we got. So there are pink and blue blobs here, and what they mean are that the early universe was not exactly the same density and not the same temperature in every place. Stephen Hawking saw this picture. He said it was the most important scientific discovery of the century, if not of all time. I thought, okay, that's pretty nice, Stephen. Why did you say that? Now I can better tell you. At the time I just felt, gee, that's amazing. Now we can say we would not be here if there were no spots on that map, because the fact that some areas are more dense than others breaks the symmetry, and it means there's enough gravity to pull the material back into, stop the expansion, pull it back together to make galaxies and stars and eventually planets. So we are here because of those spots. Number 2, most of those spots come from something we call cosmic dark matter, which nobody can see. It is actually transparent. Nobody knows what that is either, but at any rate we know it does something to this map. And the third thing is, if we ever do know what made those spots, then we might understand quantum gravity, which is a little far in the future, but it's a great hope. So it turned out to be useful and important, and here I am showing my spectrum as I did many times and getting my diploma from the King of Sweden back in 2006. So since then it's been parties and speeches, which I'm doing again today. Thank you very much, I enjoy it. But what happened after that, of course, well, COBE wasn't the only thing that we launched to check out the Big Bang story. We launched the Hubble Space Telescope in April of 1990. So it's now 33 years old. Our child is in excellent shape, of course, because we went up 5 times with astronauts to put better stuff in and to fix the focus problem. And so one of the first things they did when they got that thing fixed was to point the telescope at an empty region of sky, and astronomers saw galaxies everywhere that they did not expect. So, okay, that's really important, and what do you do next? They said, build us another telescope that's even more powerful, and I'll show you what that is. So here it is. Here's the great James Webb Space Telescope, as we imagine it to be in space, because of course you can't see it anymore. It is named for James Webb, the man who was the administrator of NASA, who went to Jack Kennedy with a plan for Apollo. and he got what he needed. And by the way, a little story to tell about that. He didn't believe scientists and engineers knew what we were talking about for the budget. So he, in the taxi cab riding over to see the president, he doubled the budget. Then it was about enough. So he had a better analysis of risk than the rest of us would have had. So we made it work. He also said, Mr. President, we need to have some science. Can I start some science labs around the country? And eventually Jack Kennedy said, yes, we'll allow that. Even though we're bankrupting the country for this project, we will do some science. And he said, well, we sent out probes to Mars and out of the solar system. So started space astronomy under him. So anyway, that's why we named it after him. Even though most astronomers had completely forgotten who he was and didn't care. Now it's much more interesting. So our main contractor is north of Grumman, which is a little south of here, mostly near LA Airport. We have 4 infrared instruments that come from Europe, Canada, and the United States. The telescope mirror is 6.5 meters across. Can I use metric units today? Yes. Okay, 6.5 meters across, which is about 2.5 times as big as the Hubble. So it's much more powerful just in collecting light. And it also does things that the Hubble could not do at all. The telescope is cooled to a very low temperature, so it doesn't emit its own infrared light, and we'll show you why we care about that. It was launched on December 25th, that is to say Christmas morning 2021, at a time when COVID was everywhere. So I watched the launch from my sofa, as most of us did. We were intentionally avoiding seeing each other, because we don't want the control room to be full of COVID. Okay, but we had a perfect launch from the rocket company. It's a European company called Ariane, and mostly in France. And they put us exactly where we wanted to go, which means we got a 20-year predicted lifetime before we run out of fuel. So very happy about that. And by the way, the launch was after sunrise, but the rocket blast is so bright you can't see that the sun was out. Anyway, there it is. Went out to the right place in sky, which we call Lagrange point 2. Now this is a special place in the sky where the gravitational force of the sun and the earth are just enough to pull the telescope around the sun once a year with us. So it stays overhead at midnight, and that's a great place to put a telescope because sun's over there, Earth's over there. We put up the umbrella, and the telescope is cold and protected from the heat behind all those things because they're all in one direction. So telescope's in the cold and it's dark, and that's what we wanted. By the way, I point out on the chart that we named these 5 Lagrange points after Lagrange, even though the first 3 were discovered by Leonhard Euler with a pencil. So now I want to show you why we want to study infrared light. So why study infrared light? Well, several different reasons. One is things like this. This is a place where a new star is being born as we speak. And this is a picture taken by Hubble at visible wavelengths, so ones that you and I can see. And there's something in there, but you can't see it very well because dust grains are in space. So you think, I thought space was empty. No, space is not empty, it has dirt. Where does the dirt come? It's from prior generations of stars that blew up, liberated the chemical elements that you see in the building. In the early universe, we had hydrogen and helium. No calcium, no iron, no phosphorus, nothing to build your house out of. But they were all formed in stars that come to the end of their lives and put the material back out into space. So we're now making new generations out of stars that have dust around them. And this is the problem that we have. We want to see inside to see how the stars are born, and we can't. But if you use an infrared light, you can see through the dust cloud. So why is that important? Well, or how does it work? Well, when you go to the airport and they look through your clothes with their millimeter scaler, that's using longer wavelengths to get around the scattering of the fibers. So we use the same trick. We go to longer wavelengths of light, and the light can go around the dust grains. So now we can see inside. In this case, we see that the star has jets coming out because that's quite often the case in brand new stars. So seeing through clouds of dust. We also see things that are too cool to light up and emit their own visible light that you could see. So here's an object called a planetary nebula, and it's called a planetary nebula, but it has nothing to do with a planet. It's just early astronomers thought it looked like one. So this turns out to have probably 5 stars down in the middle, and one of them is in the process of blowing itself up. So we can see that, and the infrared is penetrating to the inside and showing us details that we could never see. And so now, of course, we have a story about how this is working, but you're just showing you a tool that we now have to see inside cool objects and find out more about them. So, by the way, you're all emitting infrared light too. If you sit here in the house, you're actually transmitting about 500 watts of infrared power, but you're getting about 495 back from the room around you, so you don't notice it. You don't get cold. But if you were out there as an object in space, we'd be able to see you very, very far away with our telescope. So here's another marvelous thing we can do. As stars blow up, sometimes they put out pulses of material. And here's this story that we got from this one. We've got 2 stars orbiting around each other, and one of them is unstable. So when the 2 get close together, it sends out a pulse of gas and dust, and the picture on the left shows the result of periodic pulses of dirt coming out of the star. Pretty amazing. Third reason for infrared is the universe is expanding, or another way of saying it is distant objects are running away from us with great speeds. So that stretches out the wavelength of light that we receive from distant objects, and here we've got a sort of animation to illustrate that idea. So there we are, stretching out the light of distant galaxies so it comes in as infrared wavelengths, even though it started out as short wavelengths. So maybe I should have said, what's the difference between ordinary light and infrared? It's just the wavelength, the longer wavelength. So now I want to show you our first data release. This is the President Biden's announcement on July 11th last year, and it's full of marvels for astronomers. What you see, well, lots of pretty things. The thing with a bright hexagon with the 6 spikes sticking out, that's an ordinary star. So we know about them, and it's not all that interesting today. Then there's this big bright fuzzy object in the middle. See if my so-called laser pointer will point. That is a very, very large galaxy, pretty close by. And it is so massive that it has its gravitational field can bend light. Einstein told us that gravity could bend light, and it does. He didn't expect we'd ever be able to use it as a tool, but what we're seeing here is this force, the gravitational force of these big, bright, fuzzy galaxies is enough to produce distorted images and magnified images of much more distant things. So all these funny looking arcs that I'm pointing at are sometimes multiple images of much more distant galaxies magnified by 10 or 100 times. So, and we're using nature's lenses to look farther away than we could ever see before. So anyway, this is one of my favorite pictures, and we chose it for a good reason to give out to the public, and we've been still making fundamental discoveries from this picture ever since. So here's an example of the technique that astronomers use to tell how far away things are. So this is what we do is we take the picture that I just showed you, and we say, well, some of those objects are really interesting to us for some reason that we have. So get the light and spread it out into a rainbow, a spectrum, and we see the data that we took. And the important fact is marked by these vertical red lines. It's kind of hard to see in the picture, but we put a little box around each interesting target, send it into a spectrometer, and we can get up to 100 different objects and get their spectra all at once. Hugely complicated process, but at any rate, we use this to tell how far away an object is from how much the wavelength is shifted. So here's another picture to illustrate this story. And this is actually one of the most surprising results we already got. The first galaxies, those little fuzzy dots, are too bright, too big, they happen too quick, they're too hot, and nobody quite knows why. So nothing the matter with the universe, but sure is something the matter with our idea, and we have to figure that out. So I'm not ready to tell you what it means yet, because maybe we're just wrong about our story, and maybe we've been fooled in some way, but anyway, this is something that astronomers love, because there's a mystery here to explain these fuzzy dots with colors. we have measured the motions of material orbiting around a black hole quite far away. We made an apparatus that's specially designed and good for this. We can get a spectrum of everything in a certain region around a target. That's interesting. So we knew there was a quasar, that is to say a black hole where things are falling in, and we wanted to measure how things orbit around a black hole. Well, I guess everybody knows you can't see a black hole because things only fall in, they never come out. But on the other hand, as material is falling into the black hole, it gets compressed and squeezed to enormous temperatures, and we can see that. So we want to know how it works, and we want to know why is there a black hole in the middle of every galaxy. The fact that there is was a big surprise from the Hubble telescope. Anyway, so we are now able to not only see the motions, but analyze the chemical composition of stuff orbiting around a black hole. We are able to get the detailed shapes of some of these most distant objects. Here in our own galaxy, we have some marvelous things called globular clusters, like 100,000 stars all packed together closely in the sky. What we're seeing here is a highly magnified image of a very, very, very distant galaxy, and we see that it has dozens of these globular clusters in it. So now our question is, well, why are they there? And did they form before the galaxy formed, or did they form after the galaxy formed? So we're working on our story, our imagination, to tell you what is that. We have also even discovered that once in a while you can see an individual star highly magnified by maybe 10,000 or 100,000 times by that gravitational lens I was telling you about. So we have our methods. So the story here is, where's my laser pointer? This curve that they've marked here in red is a place where the magnification of the gravitational lens can become infinite. So it happens, it passes right over a star right there, and they can actually tell you that there's an ordinary star in that place and get its spectrum. So anyway, we are discovering these most amazing things out there. Individual stars seen at much like 100 times as far away as you ever thought it might be possible. So here's another picture to show you. This is a place where there are 5 galaxies in one picture. It looks like they're all close together. They're not quite. The one on the left is actually separate from the others, but it's close enough that we can see individual stars in it with our great telescope. The ones 2 in the middle are actually in the process of merging together, a giant galactic collision. So what happens when 2 galaxies come together? Well, each of them has like 100 billion stars. And the stars are small and the space is large, so the stars never hit each other. But the orbits get scrambled up. On the other hand, there is gaseous material out there that has not yet turned into stars, and that makes a big splash. So these pink arcs here are places where new stars have just been born out of the collision of 2 clouds of gas. Then the top one up here has got a black hole right square in the middle, and we can begin to study the shapes of things up there. So we're just beginning to learn, how do the galaxies grow, how do they collide, what happens then. We have a picture of a thing we call the cartwheel galaxy. This marvel is the result of a collision. The little galaxy in the upper left apparently went straight through the middle of the big one. And so you're seeing the splash ring of stuff that was kicked out of the middle of the big one. So why do we see it? Well, there was gaseous material was disturbed. It flowed out from the middle and formed a whole new generation of stars, and they're lighting up so we can see everything. Who knew? Here is a galaxy that looks like a slice through a sponge. And when we had the ordinary picture of it, it was very small and looked about as big as that circle. And we never knew that it had holes in it. So why does a galaxy have holes in it? It's because new stars are born occasionally, and once in a while they're extremely bright and hot. They push out so much energy that they push away everything around them. So there's a hole here that was made by a new generation of stars a few million years ago and shoved everything away. So another thing to point out here, notice the name of Judy Schmidt. She's in Modesto, California. She gets, I think she sits at home. She gets our data. She processes it so you can see it better. So thank you, Judy. She does a lot of these things. Here's a picture of something we used to call the pillars of creation. And it looked different when we only had the Hubble picture. Now we can show you much more about it, and you can quite easily interpret that there's a giant blast of wind coming from the upper right corner, shining down blowing things away from this material. There are new stars being born inside this dust cloud, and some of them you can see beginning to poke out, like right around here. That's a new object formed. You can calculate a lot of things. Eventually, astronomers will be able to say, look what we know. We have a model. We can tell you the properties, the velocities, the densities, the chemical composition. We think stars should be born in just the way that we're going to tell you. The story is not ready for you yet, but the material to make the story is right here. We have a picture of a new star being born right now, with planets being born around it, probably. So the picture that we have is there a bright star right square in the middle of this pattern. You can't see the star because we're looking edge on into an orbiting disk of material, just like what we call the ecliptic plane here in the solar system. All the planets are in one plane of orbit. And this time it's so full of dirt out there that you can't see the star, but you can see that it's lighting up the neighborhood. So if you would come back in 100,000 years, most of the dust will be gone, and we might be able to see the planets that are orbiting this little new star. So, coming soon, but have patience. We are observing planets around other stars directly also. We have numerous ways to do it. One is to just take a picture and see if there's a little dot near the bright star, and that's pretty hard to do. So the other method that we have is to watch a lot of stars for a long time and see when they blink. So we have a big catalog of stars that blink because a planet goes in front of the star and blocks some starlight. So we set off a year ago to start observing about 60 of these objects, some Earth-sized planets, some much larger planets. So you see in the animation that the idea is that the planet doesn't seem to block as much starlight at each different wavelength. And that would be true if there's an atmosphere in the planet and it's more transparent at some wavelengths than others. So now we can begin to do a chemical analysis of an atmosphere of a planet around another star. So the technique works. We have done it and detected some molecules in big planets around small stars. So far, we have not been able to say there's an Earth-sized planet that has an atmosphere. Of course, everybody wants to know, are we alone? And the answer is, I don't know yet. Because that's about the hardest astronomy problem we have to work on. So anyway, we're doing the observations, and gradually you'll begin hearing occasionally that they measured something and they found something. But so far, no atmosphere around an Earth-sized planet yet. Should I be surprised? I don't know yet. But this, I have now a chart, if you like, spectra. This is a chart that shows we measured the spectrum of this atmosphere around this other planet with all 4 different instruments that we have that could do it. And the answer is, it has sodium, potassium, carbon monoxide, carbon dioxide, water, and sulfur dioxide in the atmosphere of that big hot planet. And we're not too surprised because they rather expected that. But anyway, it proves the method is working. So ask again in a little while. We may have something even more interesting to tell you. We observed the solar system. Here is big old Jupiter with its red spot that doesn't look red. Well, of course, why doesn't it look red? Because you can't see infrared light with your own eye, so we have to make up the colors. We do it in basically the same way that we do otherwise. When you get your pocket camera, it doesn't have color either, but we know how to translate digits into colors. So we have the same idea here with our camera. We put short wavelengths are blue, medium wavelengths are yellow, long wavelengths are red. And so we make them an artificial color that is actually meaningful. Okay, so here is Jupiter. We have pictures of the storms. We can see different structures are different. See the satellites, even Jupiter has rings around it. You can just sort of see it here, edge on ring. There's an aurora and the North Pole and the South Pole, which is quite bright. We can see it in infrared. Okay, Jupiter, not a surprise in a sense, but it for sure is beautiful. And it turned out it was actually quite a technical triumph to measure it because Jupiter is spinning while we're trying to take a picture. It goes around in about 10 hours. So while you're watching it, it's moving. So here is NASA attacked an asteroid. This was called the double asteroid redirection test. There's a binary asteroid there. The two things are orbiting each other. So we said we're going to hit it with a projectile and see how it moves. So it did. We hit it with a big block of metal, and it made a big splash, and everybody who had a telescope that could watch it was watching. On the left, we have the picture with Hubble. On the right hand, we have the picture with Webb, and material comes flying out. Not too surprising, but we did get a measurement that says that it moved about 5 times as much as it would have moved if it were just billiard ball collisions. So now we're beginning to learn how to protect the Earth from asteroids. Not ready to defend you yet, but at least we make steps. We have observed the only big satellite in the solar system that has its own atmosphere to speak of. This is called Titan. It's the big satellite of Saturn. It has enough atmosphere to support a helicopter. So we are going to be landing a helicopter over there in 2034. And it's cold out there. It's about 70 degrees Kelvin, 60 degrees Kelvin. So that means the atmosphere has nitrogen, lots of nitrogen, as well as methane and ethane. And there are lakes and rivers and rain and clouds, and they're made of ethane and methane. So there's something, I don't know what we should call it, titanology, to study the sort of surface rocks, which are ice, ordinary water ice, and the lakes and rivers and rain. And so we're going to go prospecting to see what's over there in 2034. In the meantime, we're observing the atmosphere and its weather and clouds. We took a picture of Neptune, and we see its satellites. Since Neptune has rings around it, you see fairly faint ones there, and a very bright satellite in the top, hidden by my caption, called Triton. So we can't easily get out there to see them close up with a new probe. It takes $1 billion and many years to get out there, but we can see them now in ways that we never could see them before. We just recently got a picture of Uranus. There's his edge face on, and see it has many, many beautiful rings. And this is a reminder to tell you that Uranus is the only planet that doesn't have a spin axis perpendicular to the orbit plane. So we're looking at the pole of this amazing planet. So it's got many satellites. You can see on the left-hand side many satellite images, as well as this curious atmosphere with clouds in it and bright spots, and I think we're just beginning to interpret them. So that's a sort of summary of the Webb telescope science that I have to tell you about, and I'll have a few more things to tell you because we think we have a few more minutes before we do questions and answers, right? So you can all follow us all along on our social media sites, and if you just want to see what are the pictures of the day, Google JWST images, and there's something in the news every day. We have a blog. Every few days we post something on the blog to tell you what's the coolest thing that we got lately. So I just want to give you a short sketch of what comes next for astronomers. The next one for astronomers is a European telescope called Euclid. They're going to be looking at signs of dark matter and dark energy by surveying a lot of sky. Telescope is relatively small, about this big, but still very powerful. Coming soon, because it's basically built, waiting for launch. And they had to move to, I think, a SpaceX launch because the Russian rocket they were going to use isn't available for some reason. We are finishing up the Vera Rubin telescope. Vera Rubin telescope is going into, it's being finished up in South America in the desert. And it is a huge telescope. It's much bigger than the Webb, 8.4 meters diameter. And they will survey basically all the sky they can see from that spot on the Earth every 3 nights. So the basic story they're telling us is more terabytes of data than you could possibly imagine, and about 10 million alerts every night of something that changed. So what you're going to do? Have we got 10 million graduate students? No, but we're going to have artificial intelligence to look at the pictures and tell us which ones are actually interesting enough to follow up with something else. So on the Webb telescope team, we do expect to get a phone call from time to time. Look what we found, we got to go look at it right away. And we're set up, but it'll take us about 2 days to respond because it's people. We have to figure out what to do, send up the commands. So we are also planning to launch another telescope named after a woman. This is Nancy Grace Roman. She was the head astronomer at NASA for a very long time and was a friend of mine. Anyway, this one is to look also for the dark matter and the dark energy, which again are invisible, but you look for signs of their effects on things. And this one is also going to carry a coronograph, which is a device to look at images of other stars orbiting planets directly. So it's a hard thing to do, but it's our first very high performance coronograph. So we don't know what we'll see, but we'll get practice on the technology, and maybe it'll be better than required, and maybe we'll see something even that we weren't expecting. So that's coming. We know they're doing this, and then we have uncertainty about what's coming after that. But the National Academy of Sciences runs a committee every 10 years for us, and they tell us what they think astronomers want. And what astronomers said they want next is a telescope that's at least as big as the Webb and much more perfect, so it can see little Earths orbiting other stars directly. See the little dot, see it orbit around, and get a spectrum, see what's the chemical composition of that little planet. Does it have an atmosphere, oxygen, water, carbon dioxide, carbon monoxide, all the other things you might think would be signs of life or not life. So that's coming, and maybe now we'll stop and take some questions. So thanks very much for the coming to hear the story, and we have plenty of questions possible.
Thank you very much, John. A wonderful result. I'm sure this is just the tip of the iceberg. We're going to see many more from JWST.
Yes, I think so. We're just beginning.
So we have time for a few questions. So please raise your hand and speak loud so everybody else can hear you. Go ahead.
So you've worked on some pretty impressive technical projects, but you also have cost and schedule you have to play with as a program manager. How do you think about managing those trade-offs when you're working on big projects like this without the program getting canceled?
Okay, so how do you get it to really work, huh? So number one, I'm not a manager, so I work with real managers who know the answer to your question. But I'll just tell you the general strategy is if you don't have the right amount of money and schedule to do the job, failure is guaranteed. In our case, we were very fortunate that even though we ran out of money more than once in the planning, our Congress and our Senate said, we understand this is really important, we better go get you the money. So when we did finally launch, after numerous delays and lots of cost increases, it worked. So I asked the project manager, said, how did you make it work? We launched when we were ready, which means we did test and test and test. That sunshade that unfolded, we didn't show you a scary movie, but we unfolded it 4 times on the ground before we launched it. And 3 times it failed in different ways, and we fixed it every time, and we said, now the 4th time better be right. And there always something quite not perfect, but we fixed all those things, and then we launched it, and it worked. So rehearse, rehearse, rehearse. How do you get to Broadway? Rehearse and rehearse. That's the only possibility. You also, of course, say, we better have 2 of everything if we possibly can. And then we get grouchy committees to tell us that we might have made a mistake. And we don't really feel good doing it, but we need them to do it. So that's the sort of 2 of everything, grouchy committees, and test everything.
Go ahead.
You touched a little bit on the 6 or so galaxies you said had matured too early, too hot, and you were not ready to postulate what the reason was. But are there any leading thoughts and ideas on what might have happened? Yeah,
there's a lot of speculation. The sort of generic one is we're just wrong about something. A sort of more subtle one is we use models of the galaxies based on what we knew from Hubble. And then we look at something much farther back in time, much different conditions. Why would we expect it was correct? Should be different. So one possible reason is maybe the first stars are much bigger and hotter and more massive than we were thinking. So when we look at the fuzzy dot, you're seeing the aggregation of billions of stars together. You're not seeing them one by one. So if you don't know how to connect the brightness with a story about the mass and the age, you could just be wrong. So they'll tell you in a while. We'll have probably 7 competing explanations, and maybe one of them will be right.
Yeah, how significant is the impact of meteors on the project?
Yeah, so we actually got pretty famous for micrometeoroids. So what are they? They're little sand grains, so small you could barely even feel one if you had it in your fingers. But when they come at you at 30 kilometers a second, they would hurt. It's like a baseball hitting you. So we got one. We expected them. We knew how many there would be, and then we actually are getting the right number of them. What we didn't expect was there might be some vulnerable spot on the mirror where it would make a big bump instead of a little hole. And so we have one that hit us, and it had us, after about 6 months it hit us. So we were worried, but there has not been another one. So as it happens, the bump that it made was not so big to really bother us, so we still have performance that's almost twice as good as spec. So well, how come that? Well, of course, our engineers always have performance margin. You never build it so it's just barely good enough. You build it so it's a lot better, just in case something you don't know about happens. So this is one of those things you didn't know about. So on the other hand, now when we're going to build the next telescope that's even more perfect, we have to deal with this for sure. No taking chances.
Yeah.
Yeah, go ahead.
Okay. I was wondering what the interaction between theory and images were. Like, obviously the images inform the theories that we develop, but how much does our interpretation of images, or even the images we chose to get, how much is that dependent on our theories? And like, does that mean that we might have a confirmation bias if we're only looking at regions where, we have theories for or something like that?
I'm not sure I quite understood the question, but are you asking whether we're getting the wrong answer because of some theory that we have?
No, I'm saying like, definitely the images that we're getting are either confirming or telling us that we need better theories. But how much are our theories influencing the images that we're getting?
Okay, well, of course, we use theories to do several things. One is, what telescope should you build? What are you going to hope to learn? So we ask our theorist friends to predict what's going to be out there that we've never seen. So that helps you find out what to build. Then we have additional step when we built it. Now we say, where should we point it? So every year we ask for proposals. We just received 1,600 proposals. So we have to get lots of committees to read 1,600 proposals. And theory is behind all of them. They say, if we took a picture of my favorite object, we would learn something about a theory. So that's how it comes to work together. And eventually, the interpretation of the pictures that I showed you will become some very long theoretical calculation about we understand this.
I'm not sure this is correct in reality, but it seems like many of the galaxies that we could see before had some symmetry. Let's say globular has some symmetry, even bar galaxies have symmetry, and so on and so on. Why do some of, or many apparently, of these very ancient galaxies appear so irregular in their shape?
Okay, let me see if I can get back to them.
You want to clarify what you mean by ancient?
The ones they can see now, the ones that have become visible by JWST, that's what I mean.
Yeah, so here they are. So here they are. These are the ones you were asking about, I think. So the reason these look weird is because they've been magnified by a distorted lens.
I don't mean that.
You don't mean these?
That's clear.
Yeah.
What about the 5 that you showed where they were all behaving strangely?
Oh, yes, okay, I did show that. Let me show if we can show that one. This one.
Right.
Yeah, these are probably funny shapes because they're too young to have settled into a round shape. So why is the Milky Way round? Is because things have had time to orbit around multiple times, and so the original pieces that merged together have all been scrambled. So these parts are too young to be scrambled up yet. Could be. Ask again later.
wonderful, and I'm thinking in a positive way. How
Bit louder, please.
Okay, this is all wonderful, and I'm thinking in a positive way. How does the knowledge you're gaining help impact our daily quality on Earth?
Good question. Well, number one, we do it because people want to know the answer. So we feel good about knowing the answer. And we also feel good about, we did something incredibly difficult, and as a planet-wide civilization, we accomplished something together. So it says, if you want to interpret it this way, we can now do other projects that are equally important and bigger. Like, can't we solve the climate change problem, for instance? Can't we cooperate about something? And the answer is, of course we can. There are a few people who want to interfere with that, because, of course, not everybody wants to get the answers that we scientists are getting. But of course we can. When Jack Kennedy said we were going to the moon, he had the same question on his mind. And he said, we're going to do this not because it's easy, but because it's hard. And he also went on to say, and it will focus our energies, we'll learn how to do these giant projects, and then he promised, not quite done yet, and we'll do all the other things too, he said. So it's a little bit brave, because some of the problems are a lot harder than this. But we can do it, don't you think?
Yes.
All right, let's do it.
Yeah, this is really good. I'm curious, you said 30 years expected lifetime, so you can have a lot of proposals, and I guess you mentioned you have a lot of committees, and after 30 years, you think it'll just limp along, or you have plan B?
Oh, so he's asking about the lifetime and what do we do then? So actually, our current expectation of life is about 20 years, and so what do we do then? So either we'll have come to the end of what we think the telescope could possibly tell us, or we'll say, can we possibly service it, add more fuel to it? In principle, we could. In practice, it's really hard. So we did not design it so it could be serviced, like those little electronic boxes on it, no user serviceable parts inside. But we did paint a pattern on the end of the telescope so we know how to latch onto it with a robot if we decide to do it. So probably not going to do it because I think astronomers will say, we actually want to spend, if we can get the money, we want to spend it on the next telescope that's even bigger and better. So that's more likely. Okay.
Thank you for an amazing talk. I was wondering, what was the strategy for taking the Jupiter photo?
Oh, like how do you deal with it when Jupiter is spinning? Well, you basically have to, you take the data that you can, and then you have to put it through a data processing system so it unscrambles the motion. So it's a computer data processing. Take the picture more or less in an ordinary way and then undo it. Undo the spin in the computer.
All right, go ahead. One last question.
So you showed us a picture of a matter orbiting a black hole in a distant galaxy. That galaxy was supposedly 11.5 billion year travel time, right? So why not something closer that's going to be higher resolution?
Right, so yeah, we see plenty of them closer up as well. That was interesting because we would like to know how did they first form. So, for instance, did the galaxies form the black holes, or did the black holes cause the galaxies to grow? And so we're trying to work this out by looking as far back in time as we possibly can. That's the reason to push as far out. So we did not expect every galaxy to have a black hole. The Hubble showed us for the first time that there was one in a nearby galaxy, and now we know they're everywhere. Now, jeepers, this is a surprise. Please explain this surprise.
It seems like the telescope is designed or is very good at looking very far back in time. Have you aimed it at our own galaxy to look deeper into the planets near us and maybe discover more?
Yeah, we can aim anywhere in the sky that's not too close to the sun or too far from the sun. And so yes, everything in the solar system is available from Mars on out, and we can look at every part of our galaxy at least sometime during the year. So yes, we look at all the things that astronomers say are the most interesting. Some are close up. Yeah, so we do.
All right, let's thank John again. has agreed to hang around here if you want to come down and ask questions that you're too shy to ask.
Okay. I don't think this is a shy audience, but anyway, you're welcome to come down.
Yes,